Okay, this lecture is going to cover total energy and rest mass energy in relativity. Let's start with what we just learned to be the expression for the kinetic energy in relativity. And let's rewrite it slightly. The kinetic energy was defined to be gamma minus 1 mc squared. But let's put the gamma on one side of the equation, so there's the gamma mc squared, and the minus 1 we'll put on the other side, becomes a plus 1 times mc squared on the right side, and that equals the so it's put another way around. Gamma mc squared is kinetic energy plus mc squared. So let's write it that way. What do we learn from this? Well, first thing I notice is that mc squared has the same units as energy. Okay. That sounds interesting. And when written this way as kinetic energy plus something equals something, it looks like I'm adding something like a potential energy, where I could write that the total energy, which is now going to be gamma mc squared in this formula, is kinetic energy plus E naught, this potential energy. And that's the total energy of an object. Right, so the total energy K plus E naught, where E naught is this mc squared, which is referred to as the rest mass energy of an object and is a constant. Aha! Now we know where in pop culture is picked up from Einstein that E equals mc squared, right? It's the rest mass energy of some object with mass m. So we've now kind of rewritten our expression for kinetic energy to look like something that's kinetic plus a potential energy, which is the rest mass energy of the object, equals the total energy. So the total energy is the kinetic plus that rest mass energy. All right. Now this rest mass energy can be very large. Suppose I just have 1 kilogram, right? 1 kilogram for mass. So in SI units, that's 1. What is C? C is 3 times 10 to the 8th. But C is squared. So the rest mass energy of 1 kilogram is 1 times 3 times 10 to the 8th squared, which is 9 times 10 to the 16 joules. That's a lot of joules, right? Just for comparison, to tell you how large in joules that really is, 1 ton of TNT explosives is 1 billion calories, which is also 4.18 times 10 to the 9 joules. But this is 10 to the 16 joules, not 10 to the 9th. So we're talking about 21 megatons equivalent of TNT in 1 kilogram of mass. That's a lot of energy. Okay, but not to scare anyone, we're just saying that 1 kilogram of mass actually has a lot of energy in it according to Einstein. Now, there's one other takeaway I'd like to point out to you, is that this expression that the total energy is gamma mc squared gives you a convenient way to calculate gamma. Because if I just divide both sides by mc squared, the total energy divided by mc squared is just gamma. Now remember, in a previous lecture I told you it's best to work on your calculator using gamma and not with speed v. At least when v gets close to the speed of light. It's hard to keep all the significant digits in your calculator, but gamma is a nice one to work with. And the convenient way to calculate is just take the total energy over mc squared. All right. Now that we're on the topic of energy, let's talk about units, okay? Let me introduce a new unit to you, which is the electron volt energy unit. You may have been introduced to this already in your introductory physics. Recall that the potential energy of a particle, which I'll label by U, calculated from the electric potential V, is just given that, well, at least a change in potential energy, delta U, is Q times delta V. That's how electric potential was defined. Electric potential was the potential energy difference over the charge Q. Now, for an electron which has a charge of magnitude E of 1.6022 times 10 minus 19 coulombs, crossing a potential difference of 1 volt has a tiny potential energy change of only 1.602 times 10 minus 19 joules. Right? I'm multiplying the charge by the change in potential, which is only 1. So that's a tiny amount of joules. It's more convenient to define a new unit for subatomic particle energies. So if we're talking about single electrons crossing some potential, joules are not very convenient because they're so tiny. At least the energy is so tiny in joules. So let's introduce the electron volt unit, abbreviated EV, such that 1 electron volt is exactly this 1.6022 times 10 to the minus 19 joules. Right? So that's how we're going to define an electron volt. It represents that tiny quantity in joules. But we can also add Greek prefixes because, okay, maybe 1 electron volt's too small now. Maybe we want 1 kilo electron volt, 1 keV, that's 1,000 EVs. What about 1 mega electron volt, or 1 MeV, that's 1,000,000 EVs, or 1 giga electron volt, or 1 GeV, which is 10 to the 9 electron volts. So we can use Greek prefixes for these larger powers of electron volts, which are still, though, going to be very small compared to 10 to the minus 19 joules, by the way. For example, let's talk about the electron rest mass energy. E naught, the rest mass energy of the electron, is mc squared. The electron mass is 9.11 times 10 to the minus 31 kilograms. C squared is 3 times 10 to the 8th meters per second, so squaring that gives me 9 times 10 to the 16, which is a big number, but 10 to the minus 31 is even smaller. So the end result is 8.2 times 10 to the minus 14 joules. Well, that's a pretty small number. What would it be in electron volts? Well, the electron rest mass energy is 511,000 electron volts, which could be thought of as 511 keV or 0.511 MeVs. So it's half a mega electron volt in rest mass energy. All right, that's how you would use these Greek prefixes. Okay, now let's move on to a very important topic and result in relativity. And that is the relationship between energy and momentum in relativity. But first, let's start with Newtonian physics. In Newtonian physics, we had that the kinetic energy was 1/2 mu squared, where u is the velocity. And momentum was p was just mu. Now, if I'm talking about the magnitude squared of the momentum, p squared, remember momentum is actually a vector, and so I have to square all of its components, px squared plus py squared plus pz squared. But with this definition for the magnitude of p being mu, and kinetic energy is 1/2 mu squared, I could rewrite that kinetic energy in non-relativistic formulations is p squared over 2m. P squared is m squared u squared. One of the powers of m cancels with the m in denominator, so I have mu squared times half, so I have 1/2 mu squared. So indeed, p squared over 2m is the kinetic energy. And if we didn't have any potential energies around, that would be the total energy of the object, right? That would be E. So the relationship in Newtonian physics between E in the form of kinetic energy and momentum P is E is p squared over 2m. Now, in relativity, we have a different definition of total energy. E is gamma mc squared, the total energy. And P was gamma mu, at least in magnitude. So it's not going to give you the same formula to relate E and P. What formula would work? Well, let's square P and multiply by c squared. P squared c squared is going to be, when I square P squared, is going to be gamma squared m squared u squared. Gamma squared m squared u squared multiplied by c squared. Fine, I did that. And now let's do a little bit of algebraic gymnastics. Let me both multiply by c squared and divide by c squared. So this c squared becomes c to the 4th, but I better divide by c squared. So I have a u squared over c squared over here. All right. Now let's pull out the gamma squared m squared c to the 4th. So I pull out the gamma squared m squared c to the 4th, and I'm going to be left with u squared over c squared. But another way to write it is 1 minus 1 over gamma squared there, because 1 over gamma squared is going to be 1 minus u squared over c squared. 1 minus 1 minus u squared over c squared is just going to give me u squared over c squared. So this is a convenient way to rewrite it, and you'll see why in a moment. Because what I've written here is that p squared c squared equals e squared. This is the e squared. Gamma squared m squared c to the 4th is gamma m c squared quantity squared. So that's e squared times 1 gives me the e squared here. And then this gamma squared m squared c to the 4th divided by gamma squared just gives me m squared c to the 4th. So I'm subtracting off m squared c to the 4th here. So put another way around, just rearranging that equation. Move the m squared c to the fourth to the other side of the equation. I say that E squared is p squared c squared plus m squared c to the fourth. All right. So this is not quite the same thing as p squared over 2m, but this is the relativistic equivalent formula for relating the energy, total energy, to the momentum. But it involves also the rest mass. Okay, but if you look at that formula, there's kind of a convenient way to remember it, right? This kind of looks like Pythagorean's theorem. C squared is a squared plus b squared, the two sides of a right triangle squared and summed. So in fact, I could make a right triangle, and I could put PC along one side, MC squared along the other, and E as the hypotenuse. And indeed, for the hypotenuse squared is going to be PC quantity squared plus MC squared quantity squared, and that'll equal E squared, the hypotenuse squared. So that's one way to remember this formula, that E squared is P squared, C squared plus M squared C to the fourth, which is just like the hypotenuse of this right triangle. And so how much the length of this side of the triangle is depends on the mass of the particle. Okay, but let's write this equation yet a third way, right? There's three terms, so there's three ways to write that equation. So let me now put m squared c to the fourth on one side of the equation. That means I've got to subtract from the other side p squared c squared. So it's e squared minus p squared c squared. Okay. That is an important equation to remember. Well, it's the same equation, so it's obviously still important. But it's an interesting way to put it because the mass of the particle is a constant. The speed of light is a constant. And so we've got a constant equals e squared minus p squared c squared. So since mass is a constant and the speed of light is a constant, this is another example of an invariant quantity, another example of Lorentz invariance. Right? You learned one in space-time coordinates. Delta s squared was c delta t quantity squared minus x squared minus y squared minus z squared, or the deltas of that. Well, here's an equivalent one in terms of energy and momentum. And remember, this p squared is really the sum of px squared, py squared, and pz squared. So it's really subtracting three terms here to get that magnitude squared. So it's very similar form. An invariant quantity here, it was delta s squared in the space-time example. Here it's the rest mass energy squared is e squared minus the three components of momentum squared times c squared. So very interesting. Okay, let's go ahead and end this lecture here.